Good evening, everyone. Welcome to this Young Members Group webinar, which is one of many about recycled aggregate concrete from research to practice. I'm Andreas Sjaastad. I work as a concrete technologist at YMG, which is a Norwegian contractor. I work as a also work partly with the National Concrete Association in Norway, and also part of the Young Members Group in the FIB. Today we have João Pacheco from the Young Members Group and also Nikola Tošić from the Young Members Group, who are going to speak to us today. Let's see. Yes, first a brief introduction about the Young Members Group. The Young Members Group is a group to help you link and coordinate, or we will try to link and coordinate existing national Young Members Groups and also help build new ones if there's not one in your country. The Young Members Group will also assess options for you or other young members to participate in commissions and task groups, organization of events, symposia, meetings, and also congresses. We are also in direct contact with the Presidium in the FIB. We want to represent a platform for dialogue, debate, and networking. So we have a slogan that says network and knowledge. That's what you can learn in the Young Members Group. Most of you have heard about Young Members Group prior to this, but if you want to connect with the Young Members Group and have not been following these sites before, you can go into Facebook, facebook.com/FIB-YMG, and follow us there. And you can also join the Young Members Group on the FIB International website. If you just click on commissions at the FIB International website, you'll see Young Members Group as an own group, and then you can click on connect or with this group. Today, we are so lucky to hear from João Pacheco. He works or started recently working for C5 Lab as a researcher. He's always also has the project VP Tensile, use of recycled materials, and he's from Portugal. He was a teaching assistant from 2016 to 2019 at the University of Lisbon in Portugal. He's a member of the FIB and also the National Members Group in Portugal, which is a national member group in the FIB, the National Concrete Association in Portugal. His interests are structural concrete, reliability analysis, codification, and experimental testing. We also have Nikola Tošić. He is a Marie Curie Individual Fellow, started this year at the Politécnica de Catalunya in Spain. He was a Fulbright visiting scholar in the US in 2019. He was an assisting professor from 2018 to 2019 and teaching assistant from 2013 to 2018. He is heavily involved in the Young Members Group internationally, and also started the Young Members Group in Serbia. His interests are green concretes, servability, fiber reinforced concrete. Before we let João take the stand, general information about the webinar. There are only certain people that can speak during this webinar. We have to be invited to speak, so you can't unmute yourself and just start talking. But you can use the chat function at the side to say what country you're from, say hi to people. And if you have questions, you use the Q&A function. So if you move your mouse at the screen, you will see a panel that appears. Then you can press on the Q&A or chat. Then you ask the questions in the Q&A. We'll try to answer all of them at the end of this session. Yes, So now we will give the word to João.
Hello, good afternoon. First of all, I'm thankful for the FIB Secretariat and also to Andreas for the introduction. Me and Nikola will talk about recycled aggregate concretes. This presentation covers aspects related to research, to design, and also to industrial implementation. But before presenting, I'll just make two very short announcements. The first is related to the FIB Symposium in Lisbon. As we are all aware, the coronavirus outbreak led to some changes in planning of symposia and conferences. In our case, and this has already been discussed with the FIB, the dates will be kept as it was before, the 14th to the 16th of June 2021. The abstract submission is already open. There is just a slight adjustment. The conference will be both in person and online in the form of a webinar. This has not already been disclosed, but it will be disclosed soon on the symposium webpage. The URL is up on the left up corner of this slide presentation. I invite you all to follow it so that you'll be updated on this conference. Another thing is the consortium where I'm working now, the C5 Lab. We are doing research related to sustainability in the cement and concrete industries. There are several projects that have just begun. If someone is working on similar projects, they are invited to contact us. The website is there so that we can develop some sort of collaboration. Moving on to the topic that brought us all here, recycled aggregate concretes. This presentation is structured like this. First, we will talk about why using recycled aggregates in concretes. Then we will talk about properties of recycled aggregates, their influence on concrete mix design. After knowing the properties of these recycled aggregates and the adaptations you need to make on mix design, we will discuss properties of recycled aggregate concretes. Then we will move to aspects related to design, ultimate limit state design, deflections and cracking, and afterwards guidelines for RAC design and the conclusions. Recycled aggregate concretes is a twofold solution because it solves two problems. The first is the extraction of natural aggregates, because concrete is a widely used material. It's the most used construction material worldwide, and it includes a large amount of natural aggregates, up to 70% by volume. In the EU alone, the aggregate demand is very large, and in some regions, aggregates are becoming scarce. At the same time, the generation of construction demolition waste is also increasing. Also in the EU, it accounts for 30 to 36% of the yearly production of total waste. So this huge volume of CDW has made the European Union look at this problem and developed a directive that stipulated that by 2020, we should be reusing or recycling 70% of construction demolition waste. In the beginning, most CDWs would be recycled for road construction. Nowadays, this volume is not as large because road construction is not as big in Europe as it used to be. And in other regions, the situation is not largely different. So recycled aggregate concretes for compliance with the problem of the extraction of natural aggregates and of CDW generation. We say concrete in specific because concrete alone is responsible for 45%, roughly speaking, of the demands of aggregates by the construction industry. Also, the technology involved in the recycling of construction demolition waste into recycled aggregates and then for the incorporation of them into concretes is not that much different from that used in demolitions, in aggregate processing, and in ready-mix concrete design. And also, with the EU directive on waste, we will need to find a way to replace to recycle a significant volume of CDW, since we are only recycling 80% of aggregates, we have a large market for these products. However, incentives for the incorporation of recycled aggregates on concretes are not only met with legislation and with recommendations for recycling. Clear design guidelines need to be provided because agents of the construction sector are always skeptical about new construction materials, and this is perfectly understandable. And also, research should nowadays be focused on industrial aspects, because from a purely scientific perspective, we already know on most of the resistance mechanisms and durability mechanisms what happens when you use recycled aggregates. Another thing that is needed are proven applications that would induce confidence of construction agents towards recycled aggregate concrete. Talking about aggregates, they are weaker, they are more deformable than stone, and they are also more porous. They also have a higher degree of heterogeneity and are possibly contaminated. They have large water absorption and unfavorable geometry. All these aspects can be addressed. Talking about weakness and deformability, this has direct implications on concrete behavior. The solution is to limit the recycled aggregate incorporation ratio, and also, when necessary, to use specific factors on the equations of codes to account for their influence. As you see here on this picture, on the left you have a natural aggregate totally composed of stone, and then you have two different recycled aggregates, either made of concrete or of ceramic materials. They are weaker, they are porous, and they are not quite the same, and this contributes to heterogeneity. In terms of heterogeneity, the biggest challenge is the uncertain behavior of this type of aggregates and of concrete made using it. And one thing that needs to be stressed is that a recycled aggregate is not made just by crushing waste. There's a previous sorting and trialing mechanism. As you see there on the picture, on the top picture, the plastics, woods are removed in large quantities, then aggregates are crushed, and there are different types of processes to remove aggregates that are observed as being composed of undesirable materials. Having said that, aggregates after being produced are classified according to different standards. Most of them are based on the composition of the recycled aggregates, some others on water absorptions and density, and this allows to define limitations on the incorporation ratio based on the classification of the aggregates. The large water absorption and unfavorable geometry and roughness of recycled aggregates have a main consequence, which is the loss of workability of concrete. In terms of water absorption, what is usually made in laboratory environments is measuring the water absorption of the recycled aggregates over time, because this water absorption is much larger than in the case of natural aggregates, and it needs to be properly accounted for. After this is measured, the water content of the aggregates at the time of mixing is also measured. And knowing the two, you can estimate the water that the recycled aggregate will absorb during actual mixing. And from there, you have the concept of the effective water-cement ratio, which is not the same as a total effective water-cement ratio. And this is self-explanatory. With the effective, you subtract the water that is absorbed by the aggregates. And this compensates the water absorption in terms of the aggregates. In terms of unfavorable geometry, unfortunately, this will influence workability directly, and this cannot be compensated by calculating water absorption alone. So there are three main ways to compensate the loss of workability caused by recycled aggregates. Increasing the effective water-cement ratio, which will affect the properties of concretes. Increase the content of both water and cement. This has a problem, which is if you increase cement, you increase environmental impacts. And lastly, increase of superplasticizer content. An aspect that is different from research and practice concerns mix design. Recycled aggregates are more porous, therefore they are less dense than natural aggregates. And this means that when you do research, you want to make fair comparisons, and typically you try to maintain the volumetric proportions of the different materials. This may not be the case for water because of the increase of the effective water-cement ratio, but at least the paste and coarse aggregate content is typically kept. And this means that recycled aggregate incorporations by replacing natural aggregates are typically made by volume. In practice, it's not practical in an industrial environment to estimate the density of recycled aggregates because they will depend on the specific shipment of the recycled aggregates that you are using. And what is done is aggregate replacements by mass. This will change the relative proportioning of materials. If the recycled aggregate incorporation ratio is low, this will not have a significant effect. There are also some differences between research and practice related to grading. What is typically done in research is that you define a recycled aggregate replacement ratio and you distribute it evenly across different commercial fractions of aggregates. Moreover, in typical research, I would say more than half of it, you also sieve the recycled aggregates and use exactly the same grading distribution. In practice, sieving is not a feasible solution because in ready-mix concrete plants, as long as your aggregates comply with the gradings of standards, you accept them as they are. And also, there are logistical difficulties towards incorporating recycled aggregates across the different fractions of commercial aggregates, at least in urban centers, where there's more generation of construction demolition waste and also where you produce more concrete. Therefore, where plants that produce recycled aggregate concrete would have a larger impacts on overall recycling rates. And these constraints are related with land use, because in urban centers, the square meter of land is costly, therefore ready-mix plants are well packed, they don't have too much space. And since you need to separate different aggregate fractions, commercial fractions, in different compartments, if you replace recycled aggregates across the different commercial sizes, you would need a lot of space, which is not feasible in most plants. So in first time uses, and at least until this material is more popular, it is expected that most plants that will produce recycled concrete will mostly focus on incorporating recycled aggregates on a single commercial aggregate fraction, which is also expected to be a coarse aggregate fraction because coarse aggregates will have a lesser amount of contaminants and also will typically be composed of recycled aggregates with better properties than smaller fractions. There are also some obstacles related to the water content of aggregates. When I mentioned mixed design before, I was talking about measuring water absorption over time, the water content of aggregates, and then in a laboratory environment, precisely calculates the compensation water. And this is preferable, scientifically speaking, than using saturated aggregates, because when you use a saturated recycled aggregates, its pores will be filled with water. If it is overly saturated, it may even lead to some microbleeding near the surface of the aggregates, and this will result in a bad interface between aggregates and mortar, and new mortar. In the case of water compensation methods, during mixing, the recycled aggregate will absorb water. If the water will already have some cement within it, so in fact, what will be absorbed will be cement slurry. This will result in filling some pores and on a better interface. However, in practice, this is not a very easy thing to do, and there's preference for saturated aggregates. This is done with lightweight aggregates and with natural aggregates in some regions already, because it's easier to control the saturation of aggregates than to exactly determine their absorbed water. And also, if you are counting on water compensation, but the water will not be properly measured, after mixing and during transits, when concrete is within the concrete truck, the water will be absorbed, concrete will lose workability, and this may lead to unacceptable workability and rejection of concrete. The measurement of the water content of aggregates itself is also a problem. In research, recycled aggregates are oven dried, and this typically lasts longer than 1 day. And this is a very accurate way to predict the water content of aggregates. In practice, quick tests are used because you need to monitor the water content of aggregates that are stored outside. So water contents will vary significantly between days and during the day. And the tests that are done nowadays are not very accurate when you deal with aggregates that have water stored inside them. So this is something that still needs to be looked at. Having discussed these aspects concerning properties of recycled aggregate concretes, we know, evaluating individual properties, that most properties will tend to be worse than in the case of natural aggregate concretes. This is caused by the weakness of recycled aggregates and by increases in water contents. And the main difference is in terms of Young's modulus. When we talk about the classical mechanical properties, compressive strength and tensile strength decrease, but not that much. And there are also classification systems that consistently show that this can be correlated both with the composition of the recycled aggregates. Ceramic aggregates will tendentially result in worse concretes than when you use recycled aggregates made from concrete waste, for instance. And this can also be classified in terms of density and water absorption. Recycled aggregates that have small density and high water absorption will result in concrete with worse properties. However, this is looking at properties in individual terms. It's not the most satisfying way to judge the influence of mixed design when you think about structural design. Concrete is specified by compressive strength. So as long as you comply with that target strength, compressive influences of aggregates on compressive strengths are not that relevant. What is more relevant is the influence of recycled aggregates on the accuracy of the constitutive models that relate compressive strength with other properties. In terms of Young's modulus, this difference may be quite large. What we have seen is that recycled aggregates will result in a concrete that is slightly more stiff than concrete with sandstone aggregates. And this concrete will have a lower Young's modulus than when other aggregate sources are used, such as granite, limestone, basalt. In terms of tensile strength, results are more interesting. What happens is that when you have a concrete with an average strength, the influence of recycled aggregates will not be that relevant. And recycled aggregates may even result in a concrete with higher tensile strength than when natural rounded aggregates are used. However, as the compressive strength increases, your predictions of tensile strength will be overestimated. And this has a very clear and logical explanation, because you'll start being conditioned by the strength of the recycled aggregates, and you'll start having trans-aggregate fracture surfaces, and strength will decrease.
Hi everyone. So thank you again. Thank you first of all to the FIB and to Andreas for the introduction, to the FIB for the opportunity, and to João actually for the initiative, because it was at his idea and initiative to push for holding this webinar, and I'm really happy to and honored to be a part of it. So I will continue now with the section and then also switch back to João. I'm also very happy that we are in this kind of number of people, so I would really encourage a kind of open discussion. So please don't be shy for comments. I hope that there are many questions to be raised and discussed, even if this is all familiar for you already. So just, João, can you tell me, am I showing the slideshow properly now?
Yes.
Okay. So I will continue with the mechanical properties, and after speaking about the modulus of elasticity and tensile strength, the next thing that we also need for design, particularly now for nonlinear analysis, is the stress-strain relationship. Mostly here I'm talking about compression, of course. Here is the image just from Eurocode, like the standard prescribed relationship for nonlinear analysis. And also another mention, like we have here references for each figure, so we'll show them at the end. So later when you have available the video, you can just rewind and see where something is coming from. So it's all kind of cited. Generally, we need them for nonlinear analysis, and you see the terms in which they are defined. So we need the compressive strength, we need the modulus of elasticity, we need the peak and tensile strains. And this is interesting whether it's different for recycled aggregate concrete, and of course, what is the effect of recycled aggregates. And after all this introductory talk, you can more or less know that, of course, the aggregates will have an effect, and it will mostly be exerted through, like for everything else, through the residual, through the adhered mortar from the parent concrete that remains attached to the aggregate particles. That basically makes the recycled aggregates a weaker type of aggregate, offering less restraint and less stiffness. So generally from studies, more or less the consensus is, as in the figure that you will see here, that the ascending part of the branch is very similar. So here we have shown for, let's say, concretes that have two effective water cement ratios that were produced. On the left side 0.65 and on the right 0.5. with aggregate coarse recycled aggregate replacements of 0, 20, 50, and 100%. And if you look closer to the types of dots that are used, you will see that basically the strains increase in order of the increase of coarse aggregate replacement. So these are all, of course, normalized to compressive strength. So even if the strengths are different, we see that the shape of the ascending branch is similar. But it's all kind of translated to the right to higher strains. And this is, of course, because of the less stiff, the aggregate that is offered. We see this for peak strains, and at least in this study, we see it also for ultimate strains. So there is a kind of increase, and the amount of increase is, let's say, up to 20% for 100% coarse replacement. The question about the descending branch is a bit more difficult. There are different results in which, like in this one, in the graph here, the descending branch is more steep, but there are also others that find little differences between the descending branches. And of course, for the descending branch, there will be other influences besides the effect of aggregate. It will depend, of course, not just on the aggregate, but on the test setup, the stiffness of your machine, where you measure the displacement, the applied displacement rate, and so on. So for this, it's a bit inconclusive and difficult to say. Generally, as the graph in the bottom shows, you can see an increase, kind of linear increase with replacement ratio for both the peak strain, which are the lower lines that you see that go around around 2 per mile, and the upper one, which is the ultimate strain, that also increases from around 3.5. And that's from the previous study where I showed you like a similar just translation of the curves. And as I said, up to about 20% increase in the strains for 100% coarse aggregate. And you can consider this ductility, the ratio between the ultimate and peak strains, to remain constant. However, in the codes, of course, you will have equations that define the shape of your stress-strain relationship. And things to take into account are whether, for example, the stress-strain relationship is defined in terms of the modulus of elasticity. So if it already figures in the expression and you have corrected the equation for the modulus, then you have to compensate for it in the equation for the stress-strain relationship. If it's already a parameter, if it's just compressive strength, then let's say consider a linear increase of strains with replacement ratio up to about 20%. But I would not, for example, recommend increasing the ultimate strains, which are, let's say, 3.5 per thousand, above the code limits. So for linear analysis, of course, you would, in Eurocode, you would consider this for regular strength classes the limit. Although, as we have seen in the graphs, they tend to increase, it would have other implications for design. And for now, I would not say that we should increase above those limits. If you calculate for your stress-strain relationships lower strains, you can increase them, but let's say keep 2 per mile for axial compression as the ultimate strain and 3.5 for bending and other stress states. So another aspect that we need for nonlinear design is fracture energy. Of course, that's tested in a different varieties of ways with notched beam specimens and so on. Again, what is the effect of recycled aggregates? Now it exerts itself through the roughness of the aggregates and through the quality of the ITZ, of the interface transition zone. So generally, when you have these, let's say, bending tests, you will have failure surfaces in which either you have debonding of the aggregates from the paste, so it's a factor of the quality of the interface transition zone, or you will have a breakage, a failure of the aggregates themselves, a rupture of the aggregates themselves. And it's expectable that in recycled aggregates, being a weaker type of aggregate, this will occur more. Generally, studies find that for lower replacement ratios of coarse aggregate, again, so higher than 4 millimeters, there will be no significant effect. And this is something that you will see carry on through many properties, that lower percentages don't exert such an effect. For higher ones, up to 100% of coarse aggregates, there will be about 20% decrease. So just as strains would increase up to 20%, the fracture energy more or less 20–25% decrease. And as I said, there will be less debonding, and because the bond will be better because of the interface transition zone, but because of the weaker aggregates, we will have more rupture of the aggregates themselves. And this is just photos of failure surfaces from some beam tests between natural and recycled aggregate concretes of different compressive strengths. And here, mostly both failed across the aggregates. Okay. Now on to some long-term properties. Here, shrinkage and creep. So you saw before tensile strength, some smaller differences, modulus of elasticity, some significant differences between natural and recycled aggregate concrete. Besides the modulus, I would probably say that the biggest differences are in shrinkage and creep, and precisely because of the residual mortar attached to the aggregate particles. So it can have pretty high percentages, of course, depending on the crushing process, the quality of the parent concrete, and so on. But the mortar itself that remains attached can also carry on different influences, being partially hydrated or having undergone some creep that is recoverable or irrecoverable. And this will have important implications for design. So if we want to push for structural use of recycled aggregate concretes, and we want to use it, for example, for residential buildings applications, for slabs, this will have big implications in serviceability. So imagine you already have something that has somewhat lower modulus and higher shrinkage and creep. So you're going to have to expect differences in deflections, in cracking, and of course other designs where you need creep, for example, second order effects, buckling of columns. But okay, let's say that this will be less of a case for recycled aggregate concrete application, but for serviceability, for sure. Even without thinking of recycled aggregates, normal aggregate concrete has many influencing parameters for shrinkage and creep. You know, the mix design, the curing, the ambient conditions, for creep, the loading ratio, the aggregate type in the natural aggregate concrete, of course, and the way of performing tests, whether you are measuring also basic and drying shrinkage and so on. So even without recycled aggregates, you have a huge scatter of the results. Huge scatter of the results and huge scatter of the prediction models. So, you know, these are phenomena where the best prediction models, like the V4 model, the FIB model code 2010 model for creep and shrinkage, you know, on huge databases of results, have a coefficient of variation of 40%, for example. In, you know, in some other areas, they're much smaller, but here, you know, it's pretty significant. So another problem that we have, another challenge that we have when assessing this is also data reporting. So here I'm showing two graphs from two review studies that considered shrinkage on the left side and creep on the right side, relative between recycled and natural aggregate concrete. So basically it's a ratio between the shrinkage strain on the left and creep coefficient on the right for, you know, recycled divided by natural aggregate concrete, and then in terms of the coarse recycled aggregate content. And you can see, let's say on the left side, this kind of trend line being drawn, showing an increase, of course, with the RA content, but, you know, notice from both graphs the huge scatter. Okay, so now you can start splitting it up into different parameters, like how does it depend on compressive strength and so on. Another thing to take care of, not for shrinkage, but for creep, is what people report in studies that you're going to be analyzing. So you can see even on the right graph, like you have circles, which are creep strain. Then you can have people reporting specific creep, that is creep strain per unit stress, and creep coefficient, which can be an experimental creep coefficient, which is just the creep strain divided by the initial strain. But when you go into codes, the creep coefficient can be something else. You know, the initial strain can be the strain that is obtained considering a modulus at 28 days, not at age of loading. So you have to do all these, let's say, normalizations so that you can compare the results adequately. But even with this, you know, we can draw some general conclusions that the more we have of recycled aggregates, the more we will have shrinkage and creep. But the stronger the concrete, recycled aggregate concrete, the lower the shrinkage, strain, and creep coefficient will be. So let's say that for a regular 30 megapascal concrete, recycled aggregate concrete, with 100% of coarse aggregates, you should expect between, let's say, 30 and 50% increase in shrinkage and creep. Maybe for creep a little less, for shrinkage surely. So that would be really on average. But as I say, increasing the concrete class, you will decrease shrinkage and creep, and increasing the content, you will, of course, increase them. And I have not talked here too much that there are, of course, you know, studies that use and applications that use fine aggregate that will have an even higher percentage of the residual mortar and an even greater effect on these phenomena. So this was just comparing them, shrinkage and creep, but what if we want to predict them? I mean, to calculate them for design. So, you know, in design, let's say of a building, you start by adopting a concrete class. And what you do mostly is you calculate everything from the characteristic or mean compressive strength. So as a designer, it's not your position to know, you know, the type of aggregates that will be used, especially if it's recycled aggregates, what are going to be the contents, what is going to be the strength of the parent concrete. Even the recycling plant won't know that. So it's very difficult to know many parameters and to predict something that has such a high scatter with, you know, simple parameters. Then we have to ask ourselves, are there differences in basic versus drying shrinkage? Unfortunately, so far, you know, very few studies have split shrinkage and creep into basic and drying, meaning the one that occurs without humidity exchange with the environment and the other with. So we really can't say anything about that. Probably considering that, you know, recycled aggregate concretes are not so often produced as high strength concretes, then the basic part is not going to be so significant in any case. And another question is going to be, are there differences in horizontal and vertical scaling between the phenomena? What I mean here is The fact that I said that shrinkage and creep increase, does it mean that they just increase in value globally? So they're not 1, they're 1.5, or they develop differently over time. And this is also important, going to be very important for shrinkage, for example. And here I explain what I mean. On the left side is what is vertical scaling. So it's shrinkage, and you can see a vertical line of tau, H1. This is something called shrinkage half time. So because shrinkage has a final value, because it's determined by the amount of water in the mix, in the matrix, there's going to be a final value, and the half time is the time after which half of shrinkage has occurred. So for the two lines, the full one and the dashed line, the half times are the same. So the time evolution is the same, but only the final value is different. The dashed line is, shows bigger shrinkage. On the right side, the final values are the same, but they are reached by different time evolutions. So the dashed line is quicker. The half time of shrinkage is shorter. So what is it for recycled aggregate concrete? You have to go into studies and look at individual shrinkage curves. So reported values for individual mixes over time, and see how a performance of a model evolves. And basically what we did looking at it is we could find nothing conclusive to point towards a horizontal shift in shrinkage, but only just a vertical scaling. So just globally higher shrinkage that evolves the same. And this has important implications. That means you can use the existing equations of models that describe the development over time. So then you can propose some, and people have proposed several types of global adjustment factors. So here I'm giving examples from some studies that we did for shrinkage on the left side. So you calculate shrinkage according to a model, just as for natural aggregate concrete. So let's say the FIB model code 2010 model, and everything is based on compressive strength. You calculate that shrinkage, and then you multiply it by this alpha over FCM to the power of 0.3. Where alpha is the percentage of your coarse aggregate and FCM is just your strength of your recycled aggregate concrete. And then this increases your shrinkage. And so it shows that it's going to be increasing with increasing replacement ratio and decreasing with increasing strength. And something similar for creep. And in literature, you can find various types of these adjustment factors. So they will be maybe in terms of just one parameter, the replacement ratio, or several, but globally this is what we can have for now. And this is what some existing recommendations also adopted. Okay, so those were for the mechanical, short-term and long-term properties. Something else at the material level that's going to be very important for structures is going to be the durability of the concretes. And of course, the recycled aggregates are going to affect the microstructure that's going to be formed in RAC. And we're going to see effects on porosity of the concrete, on permeability, on capillary absorption, so on all the phenomena that enable deterioration mechanisms to occur. So the processes that lead to concrete deterioration, they're all going to be, let's say, mostly unfavorably affected by recycled aggregates. But how much for which process? There's of course going to be the effect of the water, the effective water cement ratio, because it will affect the interface transition zone, and the moisture state of the aggregates. They're all going to play a big factor. Now, the deterioration property processes are going to be different. They can be, carbonation, chloride ingress, freeze, thaw, chemical attack, and so on. And they have all been studied relatively extensively. Here I'm going to focus on two that are going to be the most important for reinforced concrete structures. So, in design, we're going to be worried about reinforcement corrosion, and that's going to be affected through carbonation and through chloride ion ingress. So these are going to be the two mechanisms that are the most important for reinforced and pre-stressed concrete structures, and which will determine basically the cover. And so what happens for these two? For carbonation, there are going to be two effects that counteract each other in a way. So adding recycled aggregates, you're going to be adding the residual mortar that in itself has the calcium hydroxide, which is good. It's the carbonation product. It's going to make the environment more alkaline, and so you're going to be putting in more of it in the mix. And now, of course, your aggregates themselves can be carbonated, the parent concrete can be to an extent carbonated and so on, but generally you're going to be introducing more of it into the mix. And you know, the more recycled aggregates you have, you're going to be basically increasing porosity. And that's going to be negative because it's going to be facilitating the diffusion of CO2 into the pores, and then the reaction with calcium hydroxide to make the calcium carbonate. So basically looking at review studies, and here I've chosen a graph from one, you can see the dependence on the relative carbonation depth. So again, this is going to be, you know, the carbonation of the recycled aggregate divided by the carbonation depth of natural aggregate. On the left side for concretes with coarse recycled aggregates, and on the right side with fine recycled aggregates. So that's also very important to see. And you're going to see this increase, but with a huge scatter. Okay, so for the coarse aggregates, looking at 100%, these dashed lines are like the upper and lower confidence limits. So let's say lower and upper characteristic values of 5 and 95%. If you draw a mean line, probably it will be at around 1.5 for 100% coarse aggregates. For fine aggregates, I mean, it looks huge, of course, but also look at the scatter for 100%. And, you know, just to comfort people, it's not very likely that some concrete producer, and, you know, João will attest to this, is going to use, you know, just 100% of fine recycled aggregates. But as an illustration, it's good to know. General conclusions from the literature is that it's a linear increase of carbonation depth with increasing coarse recycled aggregates, but not all the way. So up to about 70%. And from then on, the presence of more of calcium hydroxide takes over. So it becomes more important, up to 70%. Porosity is the main factor, the increased porosity, but then it kind of stabilizes and remains relatively constant between 70 and 100% of coarse recycled aggregates. But this is, of course, all for mixes that are compared typically by using the same effective water-cement ratio. If you take into analysis concretes of equal compressive strength, then more or less you're going to see equal carbonation depths, because, of course, the concrete with equal compressive strength, the one with recycled aggregates, is probably going to need a bit more cement, and then again more hydration, more carbonation products. What does this mean for cover, for reinforced concrete structures? Some, you know, probabilistic studies looking at 50-year service life design have found that, you know, if you have up to about 50% of coarse recycled aggregates, more or less you don't need to increase the cover. Above that and up to 100%, with about a 5 millimeter increase in cover for durability, you should achieve the 50-year service life for recycled aggregate concrete. So generally, if you want to be safe, it's, I think, perfectly fine to increase the cover by 5 millimeters if you have exposure to carbonation. As for chloride ingress, here the studies, again, here shown with some graphs for coarse on the left side and fine recycled aggregates on the right, have found a linear increase of the diffusion coefficient with an increase in recycled aggregates. So looking at the left figure and coarse aggregates, the full line, it's the mean prediction. And let's say that it's 1.3 for 100% of coarse aggregates. But the cover depends on the square root of the diffusion coefficient. So that's a very good thing. And it means that, you know, if this is 1.3, probably, you know, a 10-15% increase in cover is going to cover everything. What this means for the most, for the most aggressive environments with chlorides is that you're going to see a 10 millimeter increase in cover for 100% of recycled aggregates. So again, if you want to be on the safe side and ensure a 50-year service life for exposure to chlorides, 10 millimeters is going to be perfectly fine. Now, another thing I have to note here, and we'll talk about this at the end, the new generations of codes, at least in Europe, are probably going to enable a kind of performance-based design for durability, meaning that you will be testing something called the exposure resistance of your concrete and then classifying it to exposure resistance classes. And based on these, you will get the cover. So this will kind of eliminate the talk of differences between recycled and natural aggregate concrete, because basically you will test your concrete, you will get an exposure resistance class, and you will get a cover. So it will no longer be important if there is anything relative between natural and recycled aggregate concrete. Again, of course, if you don't want to test this and you are just doing design based on adopting the concrete, I would say 5 millimeters for carbonation and 10 millimeters for chloride ingress. Okay, so that's for my first part, and now I'm going to hand it back over to João, and he can continue, and I'll talk to you again in a little bit.
So thank you, Nikola. Now we will talk about structural behavior. And this will be made by judging model uncertainties, which are the comparison between observed behavior on experiments and the predictions of codes. This was a deliberate option so that we will study precisely from the perspective of a designer what happens when you use recycled aggregates. What I will present here are model uncertainties for bond strengths, flexural resistance of beams, shear resistance, both of elements without shear reinforcement and of beams with shear reinforcement, and then columns under uniaxial compression. Due to the absence of experiments, of a robust number of experiments in which recycled aggregates are made from unprocessed construction demolition waste, all of this is presented only using recycled aggregates produced from concrete. Starting with the bond strength, the model uncertainty that I'll present here is for FIB Bulletin 72, which is probably the most updated state-of-the-art model. And this was calculated only from lapse place data. No pull-out test was used here because, as many code committees, for instance, those of the FIB and of ACI, argue that pull-out tests are not a good measure of structural behavior. This has to do with many reasons: cover, the short bond length of pull-out tests, also that rebars are put into tension but concrete under compression when you do a pull-out test. There are many factors that make this type of experiment not suitable to assess structural performance. With lapse splice, which is presented in the figure on the left, that is not the case. You can realistically model covers, detailings that represents structural behavior. There are two main physical reasons for the incorporation of recycled aggregates influencing the model uncertainty of bond strength calculations, and they are directly related to the two conditioning mechanisms of bond strength. One is the splitting failure mechanism, which is related to radial stresses that developed in relation to the reinforcement bar being bonded. And this mechanism is limited by tensile strength. As we saw previously, the tensile strength will decrease slightly for average strength concrete, significantly when the compressive strength of concrete is larger. So here we have an influence on the splitting failure mechanism. In terms of the pull-out failure mechanism, which is a mechanism that's characterized by the mobilization of the transfer of force between the reinforcement bar and concrete, between the ribs of reinforcement and the concrete that is between ribs, what happens is that since recycled aggregates are weaker than natural aggregates, I have here a limestone aggregate, a big one, and here a recycled aggregate made from concrete. What happens is that this stone will be able to withstand larger stresses without breaking, while this one will tend to break prematurely, limiting the pull-out failure mechanism. So this type of experiments is made with meta-analysis. The database was relatively good. This is the bond strength model of FIB Bulletin 72. This is the one that was used in the model. What was found is that when you incorporate recycled aggregates, indeed model uncertainties become less favorable for safe design, because the mean value of the model uncertainty will decrease. That means that the model becomes unconservative, and the coefficient of variation of the model uncertainty will also increase. This is also unconservative. What is very interesting, and is shown on the scatter plot, is that as the compressive strength of concrete increases, the bond strength will be overestimated more, and this is a direct consequence of the premature crushing of the recycled aggregates and of the larger influence of recycled aggregates on the limitations of the tensile strength of concrete for the same compressive strength. I have to stress this. The bond strength model only considers the compressive strength of concrete. Tensile strength is not accounted for. And these findings have influence on the safety of anchorage and splice length designs, and the specific partial factor was calibrated to take into account these effects. And this partial factor is now under a new calibration because, well, the new generation of Aerocode 2 has revised slightly the equation, so a new calibration is needed. In terms of flexural resistance, we know intuitively, and since, well, since flexural strength mechanisms are already very well understood, that with common design, flexural resistance will be mostly dependent on reinforcement. And this was confirmed, and it was found that recycled aggregates will not influence model uncertainties. This was, in this study, it was also observed that the rectangular equivalent stress block, which is a simplification of the parabolic rectangular stress block, is still adequate when you use recycled aggregate concretes. And no changes from the perspective of a designer are needed when you design elements for bending. In the case of shear resistance, we report otherwise. What happens is that recycled aggregates will influence the accuracy and precision of resistance models. As in the case of bond strength, there is a clear physical reason. When you do not have shear reinforcements, aggregate interlock is a very important shear transfer mechanism. And if you have two aggregates made of limestone or granite or basalt, this will be able to withstand a large force. On the other hand, if your aggregates are recycled, the aggregate will not only have a tendency to break prematurely because it's more elongated and weaker than a natural aggregate, but also, and you cannot see here on the video, but I can assure you this is happening, you start having some sort of wear and abrasion, and, well, friction is not as efficient. This is reported when you analyze the accuracy of code formulae for the current generation of Aerocode 2, for Model Code 2010, and different levels of approximation, and for the drafts of the second generation of Aerocode 2. You can see that average model uncertainties become less favorable, they decrease, and the coefficient of variation of the model uncertainty also becomes less favorable, it increases. As in the case of bond strength, it is also observed that as compressive strength increases, the model uncertainty becomes more and more unfavorable because codes starts overestimating shear resistance more. This led to a reliability-based calibration of a partial factor specific for shear resistance without shear reinforcement. And I show here values for the draft of the second generation of Aerocode 2. As an alternative to changing the gamma C value, you can add a specific factor for recycled aggregates incorporation ratios. Also, a relevant aspect is that it is clearly observed that the model uncertainty is the main reason why reliability tends to decrease when you use recycled aggregates. Lastly, shear resistance with shear reinforcement and members under uniaxial compression have been tested scarcely, and sometimes data is not completely provided. Therefore, no definite model uncertainties can be proposed at this point in time. However, there are reasons to believe that, as in the case of shear without shear reinforcement and bond strength, recycled aggregate incorporation will have a detrimental influence on the model uncertainty. A final aspect about the ultimate limit state design concerns seismic loading. We know that elements designed for seismic actions are strongly dependent on reinforcement layout. And it comes to no surprise that the same failure pattern when you use recycled aggregates is reported in comparison to that of natural aggregate concrete. Load bearing capacity is also the same. Elastic deformations, however, tend to be larger. This is a direct consequence of using a recycled aggregate that is less stiff than natural aggregates and of the influence of recycled aggregates on Young's modulus. In terms of ductility, both ductility and hysteresis curves are similar and no scalar effects have been reported so far. So now it's the time for Nikola.
Okay, are you seeing just the slideshow or the presentation?
The slideshow.
Okay, perfect. So after talking about the ultimate limit states, where you saw somewhere that there are differences, somewhere that there are not, I'm going to be talking about serviceability and of course deflections and cracking, and mostly deflections. And as I talked about the RAC having big differences in modulus, shrinkage and creep, of course, and some differences in tensile strength, this is all going to translate into pretty big differences in deflection behavior. So here I'm showing just some of the studies that were done for long-term testing of reinforced recycled aggregate concrete beams. On the left side is a study from Belgrade, in the middle from Notre Dame in USA, and on the right from La Coruña in Spain, and some others also that have enabled pretty good analysis on several beams with different layouts, different reinforcement ratios, and so on, to conclude something about calculating deflections. Generally, you will see, of course, these are all laboratory tests. Perhaps they are not so full-scale specimens, and of course, we would be most interested in slabs, but these were all beams, of course. But they provide some valuable insight. Generally, of course, because of all that was said and some other effects, the deflections of RAC beams are pretty larger than the deflections of natural aggregate concrete beams. Of course, when you go to structural elements, it becomes more and more difficult to compare. Are you just comparing concretes of the same compressive strength, loaded to the same load ratio? What is going to be the same? Just having the same tensile stress in the tensile reinforcement and so on. But normalizing as you can, you will generally find for concretes of similar compressive strength pretty bigger deflections of recycled aggregate concrete. Now, again, this can come to horizontal and vertical scaling, the differences just in values, or also the development over time. Here is one graph from a study we did in Belgrade. So here we have two beams, natural aggregate concrete and recycled aggregate concrete, both loaded at 7 days. And on the horizontal axis is time, but on the vertical it's a kind of normalized deflection. It's the deflection at some point in time divided by the initial deflection, which was declared to be 5 minutes after loading. And we see basically an identical development over time. This is in logarithmic time scale, so it looks like this, but that's very important. So it's evolving the same over time, just as we found shrinkage and creep to evolve the same over time. So this was important to note. As for cracking, only also a kind of general conclusion. Not many people have tested the analytical models that exist for calculating cracks, but just on an observational level, there are equal or smaller crack spacings for recycled aggregate concrete, and generally equal or smaller crack widths for recycled aggregate concrete. And we can say that this can be a good thing from the aspect of durability in terms of the per penetration of gases and chlorides into the concrete. Of course, what about calculating the results? So to calculate deflections, you need a lot of input parameters. So you need material properties, which are your tensile strength, to know the cracking moment. You need your modulus of elasticity, shrinkage, and creep. But you also need something that's a structural phenomenon, and that's the tension stiffening. That's the contribution of concrete in tension between cracks. So all of these things can probably be different between natural and recycled aggregate concrete. So what we did when we looked at all of the available results, we calculated using the standard Zeta method of integrating curvatures for deflections, which is the Eurocode, the model code method. And of course, doing nothing and just calculating everything from compressive strength as if everything were natural aggregate concrete, you get a pretty big underestimation of recycled aggregate concrete deflections. So what we do then is we change equations for material properties. So for the modulus, for shrinkage, and for creep. You saw earlier some corrections for those. And even with them, still we were under predicting the deflections of recycled aggregate concrete. And we knew that these adjustments for the material properties were pretty good. Of course, the scatter is large, but it seemed to be not enough. So there seemed to be a need to also change tension stiffening. So there is the material difference, but also a difference at the structural level. And what we found that we should do, you have this distribution coefficient zeta in the method that interpolates your curvatures or deflections between the uncracked and fully cracked state. And it has this empirical coefficient beta, which is for long-term load 0.5. And we found that for recycled aggregate concrete, it's better to have it as 0.25. In that case, whether it is 50 or 100% recycled aggregate concrete, you would get then good, accurate predictions of deflections. So this was our conclusion, that there is a change also at the structural level. Then we wanted to assess this more in a kind of numerical parametric study that was done in open seas. And what we did was we tested, let's say, beams and one-way slabs. So one-way elements, beam elements, slabs of different heights. Here is just shown for slabs of 200 millimeters with different humidities, 50, 70%, so bigger, higher shrinkage and creep. Different classes of concrete, C25 on the top, C40 on the bottom, again, differences in creep and shrinkage, and differences in load. So you see, it goes from 0.52, the quasi-permanent to design load, to 0.64, depending on your quasi-permanent coefficient, C2. And this also causes difference. Then we took different slabs and beams with different L/D ratios, so span over effective depth. From 20 to 35. Of course, generally, for some simply supported element, you would probably, of course, not go over 25, for example. And then we looked how deformability changes. And deformability, we turned the deflection divided by the limit deflection for a particular span. And that limit deflection is span divided by 250 for the quasi-permanent combination. So whenever it's above 1, you have not satisfied the serviceability limit state, for example. And then we tested natural aggregate concrete, recycled aggregate concrete with 25 and 50% of coarse aggregates. We didn't even go to 100% because one, we suspected that not many producers would do it, and the other is that we suspected big differences. And this incorporates all of the changes for modulus, shrinkage, creep, even for tension stiffening through a different tension relation in tension. And you can see that the RAC 50, of course, has bigger deflections. The effects are more pronounced when you have bigger shrinkage and creep. So when you have 50% humidity or when you have a lower concrete class. But what is more important, I think, is that you see that RAC 25, so with 25% of coarse aggregate, is basically identical to natural aggregate concrete. Not only for the large L/D ratios, but for the smaller ones that are probably going to be the ones that you will use in practice. So, you know, for me personally, this was a very important conclusion to stimulate the use of recycled aggregates. So, you know, again, going to smaller replacement percentages, you're not going to see any significant differences in more or less any behavior, any structural behavior. Okay. What is happening at the level of design? How can we design these concretes? You know, we have presented a lot of research, a lot of results, and a lot of equations have been proposed and changes, but, you know, is it really translating finally into design? Can designers confidently use recycled aggregate concrete, you know, and be confident that they are doing a reliable design? Well, there are, you know, already some standards. For example, the Chinese standard, the technical code on the application of recycled concrete. Unfortunately, I really can't say much about the contents, but it is a pretty old standard, let's say, that they were very advanced on this and pushing for this very early. Then Spain has a standard that, I mean, its general standard for structural concrete has an annex that deals with recycled aggregate concrete. And, you know, if you don't want to change the properties, then you replace up to 20% of coarse aggregates. That's basically what the standard says. And that's completely in line with what we presented earlier. If you go above that, the standard requires testing. Or it gives some recommendations. For example, I know for shrinkage, if I'm not mistaken, it's, let's say, 1.5 increase. For creep, it's 1.2 when you have 100% of coarse aggregates, for example. Then there are Dutch recommendations, but these are kind of non-binding, but they are, again, just the recommendations what to do when you use, again, coarse aggregate. And there are some global recommendations like increase your shrinkage by 1.4 or 6, increase your creep by 1.15, and so on. But these are just isolated cases. What's now happening is that finally, you know, RAC will be in European codes. So work is underway and actually finalizing this year on the new Eurocode 2. So when I say this year, I mean the text itself, but it's still going to be a long process on voting on the text by individual countries and then adopting it, transitioning to it. So it's really not going to be soon, but the text will be. And a very important thing is, I think, that there is an annex that is a normative annex, so not an informative, but a normative annex dedicated to recycled aggregate concrete. And is basically the only type of, let's say, green concrete that made it with its own particular annex, which really kind of testifies to the amount of research that was done and to the interest of countries to stimulate the use of recycled aggregate concrete. So I see it very positively. And in light of this, you know, because a lot of the work is overlapping between CEN, which is the European Committee for Standardization, and the FIB Model Code 2020 will also have a section on recycled aggregate concrete that is probably going to be more or less very similar to the Eurocode version. Of course, the Eurocode will, you know, not be the only document for European countries. These concretes will need to comply at the same time with EN 206, which is the standard for concrete, which is also going to change in large part in its section. It already has a section that is for recycled aggregate concrete, but it doesn't consider mechanical properties in any way. It prescribes some maximum replacement ratios, but not dealing with the consequences on properties. Now there's going to be the job of Eurocode, but to be aligned with this EN 206, probably Eurocode is going to impose some restrictions on replacement percentages if you want to use some predetermined expressions. You know, if you want to go for higher replacements, of course, but then you need testing. So if you don't want testing, it's probably going to be some lower percentages. And because EN 206 is going to allow replacing both fine and coarse aggregates, probably you're going to see things expressed in terms of a total aggregate replacement. And that might sound strange at first, but you have to consider that the allowed replacements for fine aggregates will be very low. I think not about, let's say, 10%. And again, nobody is going to just replace, you know, 10% of fine aggregates without replacing some of the coarse. And so I don't see this as a big issue. But again, it's being done, and you know, a lot of what you saw today in the presentation is, you know, things that that are going to be there. I mean, João's work, of course, on shear, and there, you know, are going to be changes in modulus, creep, shrinkage, deflections, what I showed you, as I said, shear strength, and so on. And you're now going to be able to easily and hopefully reliably design recycled aggregate concrete structures. And we see this as a big step forward. And this webinar in part is precisely that, to kind of announce it in part and stimulate people to learn more about it and be confident that recycled aggregate concrete is a very viable material. And with that, I'm going to conclude by saying, you know, summarizing the main things that we saw. As I just said, we really and firmly believe that recycled aggregate concrete is a technically viable solution. Research has shown so much about it that, as I said, you know, for lower replacement ratios, you know, really no important effects. Even for higher, if there are effects, we know how to deal with them. That's important. There are, you know, very little things that we don't know at this point about recycled aggregate concretes. And the technical part, the application, you know, you heard it from João, it has its challenges, but now is the time to work on that. Exactly until we get Eurocode and model code and we start implementing. So exactly this, we have enabled the regulation and standardization of recycled aggregate concrete, and we're hoping to facilitate its use. What this means is that, you know, from now on, I think both research and practice will need to adapt. So research will probably have to refocus a bit more on what it is going to be doing. I think studying now in more and more detail the implications for design is going to be important, as opposed to so much experimental testing, but of course still. For example, we have not talked about fire resistance. This is another issue that is maybe not so finely determined. Durability when exposed to different types of chemicals and so on. So this will be for particular applications. And of course, the need for practice to adapt, both on the design side that will now have codes, but also on the concrete producers, which will really have to adapt and, you know, change a bit their business model probably and operations to incorporate this. And this is what João showed you and what he's working on, the industrial aspects, and ensuring, of course, the sufficient homogeneity, because, you know, this is a kind of not a waste material, but produced from waste, and by definition, the homogeneity is going to be probably reduced, and then we have to come up with efficient and cost-effective methods of ensuring sufficient homogeneity of recycled aggregate concrete. With that, we have basically come to a close. I am now showing here 1 and 2 slides of the literature. So, you know, you don't read it now, but you will see it later in the video if any of the figures interested you and you just want to know where they're from. This is the literature that we used. And yeah, with this, I would stop for now and I guess invite João to come online. And we can go through the questions that you have, and you know, let's go in sequence. And I guess after that, of course, since we are not so many, I feel pretty confident we can, you know, invite people to turn on their video microphone and just talk with us. We really want to discuss because I think we have time, plenty for everything.
Very interesting questions.
Okay.
I propose that we will answer again to those that we had already answered before.
Okay.
So, Nikola, you should start because you answered the first one.
Mm-hmm. Okay, so Vlad was, I think he was had a hat trick or more questions. The first one was the UN, it's actually the EU directive, right? Let's go back, well, we don't need to go back to the start, till 2020. Yeah, the EU directive that says that 70% of waste should be recovered, recycled until 2020. What is the picture now in 2020? What I can say is that, you know, it's very colorful across countries, with some, you know, already even from before recycling more than 90% of the waste, like I would say Netherlands, Denmark, and so on, to others that are probably, you know, 10 to 20%. I'm not here just referring to concrete waste, but let's say, construction and demolition waste. And, you know, it will have to do a lot with economic incentives in the country. Yeah, I'm hopeful that the situation is increasing. The problem is that why we need the codes, that even countries that recycled a lot, you know, people cite the market uptake of the aggregates as being very low. So, you know, in countries, for example, here in Spain, like the recycling plants end up as being landfills for the recycled aggregates. So the market uptake is something we should work more on probably than recycling itself. Of course, in countries where it's low, yes, but even where it's high, the market uptake is the thing to challenge, and that's, I guess, Joao's task now to do. But yeah, this is
mostly make money receiving waste, not by selling the aggregates. And these numbers of total percentage of recycling and reuse are a bit difficult to say, because in many countries waste is simply not declared. We should have better enforcement of what happens to waste after demolition. And some countries have huge recycled rates, and this is encouraging, because it shows that when you need to recycle it, you can recycle the construction and demolition waste.
okay. I hope Vlad will be satisfied if he's with us. Then, okay, this was just a comment. Well, there is one that you answered. Do you want something to add here about what kind of RA can or should be used? Is it concrete waste, ceramic, glass, other? Yeah, we can talk about like selection of the waste. Yeah.
Basically, standards have ways to deal with heterogeneity. They are not perfect, but they help. It is stipulated that contamination needs to be very small. And what is accepted as recycled aggregates for concrete applications, especially structural concrete ones, enforces that the content of concrete waste is large, either typically larger than 70% or 90%, and also that the content of ceramics will be almost 100 minus the content of concrete waste, because the content of all other possible materials has to be low. This is also partly addressed by CDW plants at the reception level, because they charge more to receive more contaminated material. So the market is already doing some efforts to reduce contamination, and standards as well. Then Vlad has an interesting question about curing and compaction. Do you want to answer to one and I'll answer to the other?
So, I mean, I told him the way I understood the question, but you can add. I just said that yeah, you can have, you know, challenges with workability if you're using a saturated surface dry, and that, you know, if not, and you're adding water and so on. The thing to keep in mind is, in practice, you'll be transporting by mixer for, I don't know, half an hour, 1 hour. And you will have more significant slump loss you can have than in natural aggregate concrete. So to keep in mind. Yes. But on vibration, compaction, and curing, go ahead if you want.
In terms of vibration, well, the difference in density of the aggregates is not that big. So vibration is not affected. You can vibrate it as commonly. And as Nikola said, concrete may be a little bit less workable, but that should be addressed before, with proper use of plasticizers and monitoring of the water content of the aggregates.
Okay, we're going forward now. These were still open. So how does this? Oh, sorry, I just. What about the performance of RAC subjected to elevated temperatures? And let me just go back. I think there is another. Yeah, what happens when the recycled aggregate is exposed to elevated temperature? Okay, so yeah, as I mentioned, this is something that we have not addressed. And for example, this is something even from the aspect of Eurocode, that is still being discussed, because what I talked about is the part 1, 1-1, and then there is the 1-2, which is the fire design for fire. There the situation is not so clear, and I'm not an expert in this area, so I can't say so much for the literature. What generally I know is that, again, you will see, a decrease with increasing recycled aggregates, but nothing unexpectedly significant, like that it is really unexpected or not a linear dependence. And again, the important thing will be the porosity that you get, but also the moisture content that you introduce with the aggregates. But what I can say is like a linear, again, decrease with increasing recycled aggregates, and nothing, out of the ordinary in that regard.
And a question of floods about tensile crack being smaller. Yes, this happens for a main reason. Since the tensile strength will be smaller, you will reach the strength necessary for cracking faster. So you'll have more cracks and they will be smaller for the same displacement or strain. And about reinforcement anchoring lengths, well, it will tend to increase because of the differences in model uncertainty, but that is under calibration right now.
Okay, is it any research on the fusion of recycled aggregates with geopolymer concrete? If there is, certain results will probably benefit the properties. So there are, yeah, 100%, but I'm not working with geopolymers. I really can't say. It's going to be a different thing, of course, because you're introducing the residual mortar, and now you are no longer dealing with hydration. So it's a different kind of animal, the concrete. And you are getting, I guess, even more interface transition zones between the recycled aggregates and the new matrix. So, now there's the mortar from, the cement mortar to geopolymer matrix interface, the one in the aggregate itself and between the natural aggregate and the geopolymer. And yeah, it's probably going to have an effect. I'm not so familiar with this topic. Usual.
Well, the same. It's not my area of expertise. I know there's some research going on, but I cannot give you results.
It will be interesting, especially that we will be having geopolymer concretes. I don't know actually if there is any research on recycled geopolymers. So what are the aggregates obtained from recycling the geopolymer? That would be an interesting thing, because it's what I can say is like creep and shrinkage are going to be very different. Carbonation is basically going to be completely out of the issue, and yeah, it's probably an interesting thing. I don't remember seeing anyone recycling geopolymers, but I guess it was done, but not so much.
Then we
okay,
have
this one was
before.
Okay.
And we have a question by Vlad. On a scale of 1 to 10, where is people's knowledge about this material? Well, I would say current knowledge is low. It could be a 3, and construction agents are skeptical. However, every day they already deal with many of the issues that recycled aggregates has, because natural aggregates are also variable. You can never be certain of how the industrial processes will go on. And well, with the timings of ready mixed plants, they need to adapt quickly to surprises, and they already do that. So I would say that from the perspective of a construction agent, it will just be a matter of time, and we are not advocating anything extraordinary. If you recycle just a small percentage of recycled aggregates as natural aggregate replacements, with the overall volume of production of concrete, you're already making a huge impact. And this is easily achievable.
Okay.
The next question is directly for you, Nikola.
Yeah, can you please elaborate on the usage of fibers along with recycled aggregate concrete? Yeah, that's the topic of the project here that is, well, hope to start now after the state of emergency and the COVID crisis. But yeah, there was research, not so much on the structural level, but more like for pavements and so on. Let's say foundations and so on. There will be effect, of course, in the tensile constitutive relation. You will, as you saw first, having the lower tensile strength, but then another thing which you also saw, the lower fracture energy. So again, you're going to have a kind of weaker type of concrete, so a deterioration of the constitutive relation. But again, nothing out of the so much ordinary. Is going to be important for long-term effects. Of course, the creep, which of course is now going to come into effect even in the tension part, affecting the bonding of the fibers, and especially if you're having the synthetic fibers. So it's something to be careful, but it's not still on a level that is advanced for any design recommendations. So like the Eurocode will only be dealing with reinforced and pre-stressed concrete in a little way, but nothing on fiber reinforced concrete, even though there will be like part of the code for fiber reinforced concrete. There are no particular provisions for the fiber reinforced recycled aggregate concrete.
Okay, now a question by Senthil Kumar about washed sea sand for concrete. It has been tested. It's a new trend right now. Their research on this topic is emerging. There is, however, something that you should keep in mind, and this also answers to the question of Juan Daniel Cassiani about the chloride content on waste, which is concrete is specified with maximum contents of chloride if you want to use reinforcement steel. So if you want to use sea sand, you need to monitor, or seawater, which is another topic of research. You need to monitor chloride contents, and on some of these investigations, what is made is reinforcement is of FRP polymers, so that corrosion is not an issue. About Juan Cassiani's question, elaborating a little bit more, the standards for aggregates stipulates that chloride content needs to be tested. On some recommendation and specifications for recycled aggregates, these tests need to be made in shorter time spans than in the case of natural aggregates. And this is to detect this type of situations, because if you go above requirements and specifications, you cannot use that aggregate.
Thank you. What about the addition of Flyash in the mixes consisting of recycled aggregate concrete? Yes, we had studies of these, and well, the effect will remain of Flyash, of slower hydration, of slower compressive strength gain. You're generally going to see trends that you get with the regular, you're going to see a linear superposition of the effects. So it's not going to be something that the effect of the two is going to be above the separate effects of one and the other. You're going to see probably lower shrinkage and creep just because of the Flyash. And all of the other effects that you would just get with Flyash, you're still going to see them. So, just comparing the natural aggregate concrete with this, probably even lower tensile strengths and other properties, but nothing on top and above what you would see separate for one and the other. But I would say an important thing probably would be benefiting the shrinkage and the creep.
Now, a question by Vlad about the costs of the cubic meter of natural aggregate concretes and recycled aggregate concretes. Well, this will depend on transportation distances, because if your construction demolition processing plant is near a ready mixed plant, you will save money on transportation. And also, and if you allow me to say this, you are asking the wrong question. because you should not be worried about the cost of cubic meter. When you use recycled aggregates, sometimes you will need a bigger volume of concrete because of deflections, because of reliability concerns. And this is not favorable for recycled aggregate concrete incorporation. So summing up, the answer is that it depends on the specific type of design, and it depends on from where natural aggregates are coming from and from where recycled aggregates are coming from.
Yeah, exactly. This is a thing that we didn't go into, but then a whole body of literature on the life cycle assessment of these concretes. So, you know, highly dependent, as João said, on transport distances. So you're going to want to produce them close to the place where you're going to use them. Fortunately, you know, most of the waste will be in urban centers and most of the new construction will be in urban centers, so it shouldn't be so high of a transport distance, but this is the big factor. And also, of course, what he said, you know, imagine we talked about deflections, so maybe you're not going to need a slab of 200, but 220 millimeters. In this instantly is not a benefit. You can go solving it with reinforcement, but again, it's increasing your carbon footprint. So you have to be really picky about the types of elements in which you put it. So it's probably going to be also a matter of an optimization within the project of, you know, in which elements you're going to use it, taking into account the exposure conditions and the structural behavior. Okay, is there a standard classification of recycled aggregates? Because the quality may differ significantly, maybe the replacement percentage won't be the dominant factor. But replacement will be a factor for concretes. For the aggregates themselves, it's what you, João, were talking about, the EN, what was it, 12620, right? For classifying by content. You want to say a bit just more about that?
Well, there's classification systems, some based on density and water absorption. The ones typically present in standards are based on composition, and they stipulate maximum recycled aggregate incorporation ratios in terms of the composition of the recycled aggregates. And they also specify maximum environmental exposure classes, also to account from some unfavorable synergetic effects of some types of recycled aggregates with environmental agents.
Okay. Is there a term called shape factor related to recycled aggregates? Well, I guess the same one like shape index. What was it that applies to normal aggregates is applicable? Yes. I'm not sure.
Yes, we have both the shape index and the flakiness index of common aggregates. It's not, recycled aggregates are not something exactly new. They are just like natural aggregates, but with slightly different composition and properties. So there's no reason to force construction agents to do different types of tests.
Yeah, I hope this answers. Vadiraj, maybe you can type a bit more what you meant, if this is that. But the standard, you know, tests on aggregates, flakiness, shape factor would be applicable. Okay, is there any difference between the alkali-silica reaction in NAC and RAC? Okay, so sorry?
No, go ahead.
No, I just wanted to say that, yeah, it will depend also highly on the, you know, natural aggregate that you are introducing through the recycled aggregate that probably you're not going to know as a factor, but yeah, also go ahead.
It's my answer is very similar to yours. It depends on the natural aggregates of the natural aggregate concretes, and it also depends on the natural aggregates of the recycled aggregate concretes and of the other components of the recycled aggregates. They may be more prone to alkali-silica reactions or not, but as in the case of natural aggregates, you can use the same tests on the aggregates themselves to check how
so you're
suitable recycled aggregate is.
You're going to want to test using the same tests and see, and here comes into play the importance of ensuring homogeneity of the product from the plant. In what way the impact resistance of recycled aggregates affects the compressive strength of concrete? Impact resistance, do you mean like crushing value, or I'm not sure what would be the... Do you know, João, impact resistance?
I would assume it's either the crushing or an analog meaning.
Okay, crushing value, yeah. Well, I mean, you're surely going to be able to draw a correlation between the crushing value and the effect on compressive strength, but honestly not in some really generalizable way, so that you really can extrapolate just from this to make it a predictor of compressive strength. Not really, but once knowing your aggregate, and as for everything else, like you have your batch of aggregates from the plant, doing a few trial mixes and drawing correlations up from there, it's going to help you a lot to do other calibrated predictions. So this, of course, I think it will have a large correlation with the compressive strength, but locally. So locally doing trials, then you could probably extrapolate, but not general, like saying for this crushing value, expect this decrease in compressive strength.
Yes, this is something that will be relevant for high strength concrete mostly, because if concrete strength is not, if your concrete mix design is not that demanding of the aggregates, if the cement matrix is weak, the aggregate crushing value will not be relevant. The mortar will break before the aggregate.
Okay, so I think I closed all here. We in the chat, you answered to Juan, and okay, we also had the hello from Vlad.
I think we have covered.
Oh, sorry.
I think we have covered everything. Oh, there's a last one.
Oh, maybe it's not the last one. Let's see.
Well, it does. It does both with natural aggregates and with recycled aggregates, because interfaces are weaker for larger aggregates. Okay, in terms of recycled. Typically, your larger recycled aggregates will be better than your your smaller recycled aggregates. Wouldn't you agree, Nikola?
Yeah, absolutely. That's I mean, the fine aggregates will, in percent, have much more of the residual mortar and will make them weaker. So, and as we saw, like the literature was mostly coarse aggregates, and okay, even within the coarse aggregates, talking with them, the higher the size, the better, but definitely a huge difference between the fine and coarse.
Okay.
Okay, so, is there a last one, or?
I don't think so.
No, I mean, we have, yeah, and the time slot is for another 15 minutes, but
and if there's something else that you want to know, you can send us an email.
Absolutely, yeah, there were you will see on the first slides that Andreas showed our emails. The video in some time from now will be up on the FIB's YouTube channel. So you can, rewind, go back and forth and see the particular things. You saw the references. Oh, thank you, Vlad. Yeah, absolutely. Let us know for anything that you need, and we are both, continuing in this topic in different ways. So even think we're open to collaborations, and we'd be very happy to hear from you. And of course, about the young members group, anything you're interested about that. And yeah, that's it, and hope to see you in person or online, but better in person in Lisbon next year. So everybody, please, you're invited to the great symposium and the young members group event that João will prepare.
Yes, check the website of the FIB symposium in Lisbon. It's very easy to find. Abstract submission is open. And if there's any doubt, anything else, please send us an email. And thank you for your attention and for being here. Not physically because of coronavirus, but
yeah, next time.
Yeah, that's. So I think this is it. Good afternoon, everyone, and thank you so much.
Yeah, thank you. Bye.